Thanks, Andy. Yeah, so I'll be talking about extension complexity and what that is, kind of an introduction into how it works and how that relates to my honours project. So the first thing I want to talk about is kind of just some background into why we even should care about extension complexity and how it's useful. So I'll be talking about linear programming and its applications, and then how that brings motivation for a definition of extension complexity. After that, I'll be talking about some famous proofs and results in the area of extension complexity and how they can be used to bound those values. And then I want to apply those tools on a simple problem. And then, time permitting, hopefully I can talk about how you can extend those results into what I've been working on. So for first, linear programming, I think it's best to introduce linear programming with a motivated problem. So I'm going to talk about a person opening a baking stall, and they have 2 ingredients that they can use. So they've got access to a certain amount of sugar and milk, and then they've got 2 recipes, which require certain amounts of that, and they'll sell for a certain amount. And the question we want to ask is, how do we maximize our profits by making certain amounts of cakes and cookies? So before we even talk about kind of solving this problem, it's best to represent it mathematically. So we can let x be the number of cakes we make and y be the number of cookies. And we can start to try to represent the physical constraints of the problem mathematically, right? So we only have access to a certain amount of sugar and a certain amount of milk, and we can find explicit formulas for how much milk and sugar we use based on the number of cakes and cookies. So for milk, we have 2x plus y, and then for sugar, we have 0.8x plus 1.2y, and that translates nicely into these linear constraints. And then we have a third equation based on how much money we make given a certain amount of cakes and cookies, right? So we've got 20x plus 15y. And we can view this as a shape in the real plane. So I should say that there's 2 extra constraints that we implicitly have here, and that's that x and y are non-zero. We don't want to make a negative amount of food. And so we've got this shape defined by these straight lines, and we want to find the maximum value of some linear function within them. And that's essentially what linear programming does. You've got a set of linear constraints, and you've got some linear function, and you want to optimize over the space. And if we solve it for this particular problem, we'll notice that we get $212.50. So I'm not going to go into details about this problem in particular, but you'll notice you have to make 5/8 of a cake here, which is a bit of a problem. So there's a subset of linear programming that deals with integer solutions in particular. But it's worth noting that this algorithm is a continuous optimization problem. It's not necessarily going to give you an integer solution every time. And more formally, you can denote this space by all x in some d-dimensional space, satisfying this matrix inequality. So essentially what this is doing is each row in this matrix encodes a specific linear inequality, and then you just combine those to get the matrix representation. So that's what linear programming is, but we can't just use it for those problems. It's a very, very generic problem-solving solution. So it works for any convex polyhedra. So any sort of shape defined by these linear half planes is always going to give you a convex shape, and also any convex shape is going to be equally able to be defined by these linear constraints. It has a lot of actual business applications. I'm not going to get into most of the details, but a famous example is train timetabling. So you can think of the throughput of a particular station being having a linear relation between the trains going through and the people that get on them. So it's very ripe for optimization. And most importantly for me is that if you're looking at a particular convex polygon and you want to optimize some linear function, it turns out that the extrema, well, we can always force the extrema to occur on a vertex of that polytope. And that means while we're using linear programming as a continuous optimization solver, if we have some discrete set of points that we want to optimize over, then what we can do is take the convex hull of these points and then optimize over that shape instead, and we know that the result is always going to be one of the points that we started off with. So that means we can deal with a number of combinatorial objects and then generate these shapes based on these combinatorial objects and optimize over that. So a simple example might be the spanning tree of a graph. So for those who haven't done graph theory, a spanning tree is just a collection of edges in the tree such that we've got no cycles, and between any 2 points we've got a path between them on the edges selected. And we can represent this as a point in our space by assigning a variable to each edge. So we've got 10 variables here, and then we're going to give a 1 or a 0 in the tree dependent on whether the edge is in the tree or outside of the tree. So edges that are in the tree will give a 1 here, and edges outside will give a 0. And this point, or this tree, is represented as a singular point in this 10-dimensional space in this example. So then we can consider the shape defined by taking the convex hull of all possible spanning trees of a particular graph G. And then we might ask, well, what's the point of having this polytope? You know, what do we actually do when we try to minimize some linear function over this space? Well, a linear function is going to be the form of this, where we've got some constants w multiplied by each edge, and then we're going to sum up each of those values. And we'll notice that, well, for a particular tree, what we're doing is actually just summing the w values for edges which are in the tree. So we can think of this as weighting each edge in the graph. And then what we're doing is summing the weights in the particular spanning tree that we're looking at. So if we minimize over this convex shape, what we're actually finding is the minimum sum of edge weights for any particular spanning tree of G, or otherwise solving the minimum spanning tree problem, which is a very popular and a very useful algorithm to be able to solve. So it's got applications not just in continuous optimization, but actually also in discrete optimization. And that kind of motivates the definition of extension complexity. So if we can define our polytope by a polynomial amount of constraints, then it turns out that we have an algorithm that we can solve this problem in a polynomial amount of time. So we're very interested in, for a particular problem, if we can embed our problem in a space with as few constraints as possible. And you might naively think that well, the solution to this is always just to use as low a dimension as you can, but it turns out that this actually isn't the case. A simple example is this example here. So we've got an octagon in 2 dimensions, and we need 8 constraints to define this octagon, right? We have 8 sides, but we can actually view this octagon as the shadow of a 3-dimensional twisted cube. And you'll notice that the kind of the points on the cube line up with points on the octagon, but we've actually only required 6 of these planes to define our cube. And what that means is that if we wanted to solve a linear programming problem on our octagon with some linear objective function, what we can actually do is use the same linear objective function on our cube, solve it on the cube, and then project down onto our 2-dimensional plane. And this means that while we might have started with, say, 8 constraints that we wanted to run on the LP, we can instead do it by solving a problem with only 6 constraints. So for a particular polygon P, this higher dimensional shape that's projecting down is called an extension or an extended formulation of the original polytope, and the extension complexity of a polytope is exactly the minimum possible size of an extended formulation. So in this case, for the octagon, we know that the extension complexity of the octagon is going to be less than or equal to 6, because we've given an example where an extended formulation could map down with only 6 constraints. I mean, I think from here, given that we care about linear programming, it's pretty obvious why we should care about extension complexity. Because we want to solve these linear programming problems, we're interested in solving them as fast as possible, and therefore finding the smallest kind of size polytope that we can embed our space in. As we'll see in a second, the extension complexity of a polytope is equivalent to a lot of other properties in different areas of mathematics, which seemingly seem disjoint, but they show up anyway. And that leads to some very, in my opinion, beautiful and creative proofs. But not just that, extension complexity is, it does have some interesting results. It's not completely obvious what it is when you're looking at a particular polytope. There's some examples here that I won't get into where the extension complexity of a polytope might be exponential, and the original polytope was also exponential size, but there's also examples where you start off with an exponential size polytope, but the extension complexity turns out to be polynomial. So we can come up with some very, very compact formulations based on some seemingly very complex shapes beforehand in some cases, but not always. So the first tool in our toolbox is the slack matrix, and probably the most basic. So for a particular polytope, we're going to define this matrix where the rows in our matrix correspond to these constraints or planes that define our shape, and then the columns in the matrix are enumerated by the vertices on the polytope. So in this case, we've got 3 constraints and 3 vertices, and what the entries in the matrix are is essentially a scaled version of the distance between that particular vertex and the constraint defining it. So this particular constraint can be written as a row from our polytope definition of the matrix, and this might be, say, ax is less than or equal to b, this area up here, and then on equality we have this line. What we do for the slack matrix entry is just take the right-hand side minus the left-hand side, substituting in our vertex. So this gives us our slack matrix, but the slack matrix that we've calculated isn't going to, well, there's a few options that we had when we were calculating it. First of all, we can enumerate the vertices and the constraints any way we like, right? So we can permute rows and we can permute columns. And the second thing we can do is multiply constraints. Now, this follows from the fact that, say, x being less than or equal to 2 is the same as saying 2x is going to be less than or equal to 4. But the scale distance between those two sides is going to double. So we can also multiply any row we want by a constant factor. And on first glance, this doesn't actually really seem to encode too much information, right? We're starting off with just kind of distances between vertices and constraints, and even then it's not the actual distance, it's some sort of scaled distance compared to the other vertices. But it doesn't seem to tell us much about the actual structure of the shape. But it turns out we can do a fair few things with it. The first thing is trying to factorize it. So if you've done linear algebra before, you'd be familiar with the rank of a matrix. So the rank of a matrix can be defined as the minimum number of rank 1 matrices that you can use to sum up to m. And in this case, and a rank 1 matrix in this case is a column vector times a row vector. But because the entries in our slack matrix are non-negative, we want to talk about a non-negative rank of a matrix. And the non-negative rank is very similar in definition, except these rank 1 matrices have to also be non-negative, and we have to sum them together. So this is a small case where actually the non-negative rank isn't actually the same as the rank. And crazily enough, we get a theorem that the non-negative rank of the slack matrix we just defined is actually exactly the same as our extension complexity, which I think is worth stepping back and just noticing, like, well, first of all, we're dealing with these high-dimensional objects and shadows of those objects, and somehow we can bound the size or the complexity of those objects in the same way that we can bound the sum of this matrix into these simple rank 1 matrices. But in actuality, computing the non-negative rank of a matrix is generally quite hard. So oftentimes we'll just use a bound on this. So if we can bound the non-negative rank from above or below, then we can bound the extension complexity from above or below. One way we can do this with is the rectangle covering number. So the rectangle covering number is very similar to the non-negative rank, except rather than considering all of our entries, we just care about whether they're positive or whether they're 0. And then we want to write this as the sum of some rank 1 matrices, where the rank 1 matrices are also positive or 0, right? So you tend to avoid cases where you've got these complicated collections of different numbers, and you can just consider them as these big squares of positives and zeros. So that's one tool in our toolbox, and it also gives rise to a few other equivalencies. The first of these, and probably, I don't know, in my opinion, the most outlandish but the most fun to use, is communication complexity. So for a particular matrix, communication complexity or a communication protocol is essentially a way to play a game with this matrix. We're going to have two players. That's going to be Alice and Bob. And Alice and Bob are both going to know the matrix that they're dealing with beforehand. So Alice is going to get a particular row index, and Bob is going to get a particular column index. And what they're trying to do is send as few bits as possible to each other and trying to compute the value in the intersection of their row and column. So one simple way they can do this is just send the information they have over to the other person. So Alice can encode her row using 2 bits, and then send that over to Bob as a 0, 1, and then Bob now has the row index and the column index, so he can just look up in the matrix and output that value. So that's an example of what a protocol might look like. But the other thing that we get in this equivalence is that Alice and Bob both have access to a random number generator, and a protocol is considered fine if the expected value for any row-column pairing is going to be correct. So in this example, Bob could output 3 with probability half and 1 with probability half, and that would still be considered an okay protocol. More formally, you can define these protocols as rooted binary trees, where each of these vertices in the tree has a state, as an Alice or Bob node, and that essentially defines whether Alice is going to send a 1 or a 0, or Bob is going to send a 1 or a 0 to each other. And then each of these edges have these transition probabilities. So Alice and Bob can essentially use this as like a lookup table. So if Alice, for example, has the third row in her matrix, you can look at the third value here and say, okay, I have a 50% chance of sending a 1 and a 50% chance of sending a 0. And then similarly, they look up here for their outputs. So Bob on the first row might output 4 in this particular case. So that's the formal definition. And it turns out that if we look at all possible ways that we can play this game, or all possible communication protocols, if C is the minimum number of bits we need to actually play the game correctly, then we can sandwich the extension complexity between 2 to the C minus 1 and 2 to the C. Which again, it's crazy that that shows up. And I think it's really cool that we start off talking about these high dimensional shapes and how they project down as a shadow, and we can somehow limit the complexity in the same way that we can play this game on a matrix. But this one's particularly useful because if we can come up with a particular protocol, not just the minimum size one, this still gives us an upper bound on the extension complexity, right? So if we can find some way to play this game that only sends d bits, then we know that the extension complexity of the associated polytope is going to be less than or equal to 2 to the power of d. So that's kind of the tools we have access to when solving these problems. So we'll give a problem a shot now in the form of a spanning tree. So we've already dealt with the spanning tree and the edge constraints here. So it turns out that the spanning trees of a graph actually form a Metroid, and this gives us a nice result when it comes to linear programming. It actually just gives us a polytope definition outright. So these first and third constraints are quite obvious. So with the third constraint, we're just ensuring that the values at each variable is going to be non-negative. And the first constraint is just saying that, well, if we sum up all of these values, we should get exactly the number of vertices minus 1. And if you've got a tree on n vertices, you know you're going to see n minus 1 edges. So that's where that constraint comes from. The second one is the more complicated one, and it's looking at any particular subset of vertices, and then we're considering the edges in the induced subgraph. So we've got these red vertices that we've selected. Then over all of the blue vertices, if we sum their values up, we should expect that the total sum doesn't exceed the number of vertices minus 1. And what this does is it essentially breaks cycles within that subgraph. If you had a cycle going around here, these 4 vertices would have 4 edges, but we only allow the sum of all of these edges to be 3, and so we can't have a cycle of integer size in this subgraph. So this definition works, and it defines our polytope. So we could run a linear programming algorithm on this, but it turns out that this only has, or this has a constraint for every subset of vertices, right? We have 2 to the power of v constraints, so it's not very feasible to run an algorithm on this shape. So hopefully we can do better. And in fact, we can prove such a thing by using communication complexity. So the slack matrix on this particular polytope is going to be given, well, Alice is going to get a row in our matrix, which is going to be a constraint here. So the only interesting case is this 2 constraints. I'm going to assume Alice gets one of these, and then Bob is going to get a tree, right? He's going to get a vertex on the polytope, but we've chosen this polytope to be the convex hull of these trees. And so we know that a vertex on the polytope is exactly going to be a tree on our graph. And what we want to do is compute the slack. So the slack is going to be the right-hand side of this constraint minus the left-hand side. So the number of vertices minus 1 minus the number of edges in the induced subgraph on S. So Bob is going to have this tree here. Then Alice is going to have some subset of vertices on this tree. And then what we want to do is look at the edges in this induced subgraph on the tree. So the first thing to note is that this induced subgraph is always going to form a forest because it's a subgraph of a tree. And one thing we know about forests on n vertices with C components is that the number of edges we see is going to be n minus C. And so we can substitute that to simplify our slack equation greatly. So since this is the number of edges in our forest, we can write this as the number of vertices S minus the number of components C. And we find that the slack we want to compute is exactly the number of components in this induced subgraph minus 1. So now, as long as we can come up with a protocol that computes this value in an efficient amount of bits, then we can come up with an efficient extended formulation of the spanning tree polytope. So the next thing to notice is if we root Bob's tree at a particular blue vertex, we'll see that as we go down the tree, well, each of these other components kind of have a root to them. They have a root vertex, which is highest up the tree. And for all components except this one that we've rooted at, there has to be a parent edge then coming from this root vertex. So we've got these red edges that go down the tree from a black vertex to a blue vertex. And so there's a one-to-one correspondence between values in this equation contributing to a positive slack and edges in this induced subgraph, in the tree contributing a red edge, so from a black to a blue. So as long as we can come up with a communication protocol that counts these edges, then we're going to have a valid protocol. So that motivates our definition. So Alice is first going to send a random vertex in her set S over to Bob. And then what Bob's going to do is he's going to root the tree at V. So he's going to root the tree at this blue text, for example, blue vertex. Then what Alice is going to do is she's going to consider the set of all possible edges that could be read. So that's all edges in the original graph, not the tree, that go from a black vertex to a blue vertex. And then Alice is going to pick a random one of these edges and send it over to Bob. Now what Bob can do is he can check if that edge is in the tree, and if it is in the tree, if it actually goes down the tree. And if it is, the edge is definitely red. So Bob can respond with a 1 to signify that, or a 0 to signify that it wasn't red. And depending on that result, Alice is going to output the total number of choices she had at the start, right? If it was in the graph, or she's going to output 0. And what that does is, well, we know that there was C minus 1 red edges that we could have picked out of A. And we know that there was, in each of those cases, we output the magnitude of A. And so the expected value of our protocol, given that we randomly selected one of these edges, is going to be equal to C minus 1, or the slack that we wanted. So this is a valid way to play the game with a very small amount of bits that computes the slack. And in terms of how many bits we sent over, well, we had to encode a vertex, an edge, and then a single bit. So you can show that the extension complexity of our polytope is bounded above just simply by the size of the vertex set multiplied by the size of the edge set, which is obviously a lot better than the exponential bound that we started with. So we've shown that such a thing exists, but I guess we haven't given a polytope that we can actually run an algorithm on. So there is an actual construction for the spanning tree that we can show. And it starts off in a very similar sense. We've got X being variables representing edges in our graph. And then we introduce these new Z variables. And what the Z variables do is that essentially for any particular vertex K assigns a direction on each of the edges. So we've got the first and third constraints very similar as non-negativity and the sum being n-1. But now what we're doing is for each K and each edge E, we're going to direct that edge from I to J or J to I. Right, so we're going to pick a particular vertex K, or loop over all possible vertices K, and then for our tree we're going to direct the edges essentially to go up towards K. And the realization to make is that the spanning tree is the only subgraph for which, for each possible K, the out degree of all of these black vertices can be 1, and the out degree of K can be 0. Right, so each of these vertices has a parent that point to, but K has no parent. And you can prove that the other way, that integer points in this polytope are actually trees by showing that, well, for your particular xe, you have to be less than or equal to 1. If not, then you can say that xe is going to be equal to 2 or greater. And then we have zkij plus zkji. And we have a few cases. Either one of these exceeds 1 as a value, which would then break one of these two constraints. Or we have that, well, both of these, essentially we've assigned a direction in both ways, right? And what we can do in that case is consider K to be one of these vertices that we're directing from. We can't have an out degree of 1, which means we have to have a 0 in one of the directions. So that breaks that case. And then now that we know that it's a collection of edges, we can show that edge set has no cycles just by noting that if we put K on the cycle and we try to direct each of the edges, there's going to be somewhere else on the cycle where we're going to have out degree 2 pointing towards K. So this is somewhat of it goes through most of the proof that spanning tree polytope can be written as this. And then this goes to my result, where I mentioned before that spanning trees form Metroids. Well, there are a few other graph Metroids where the polytopes are interesting. The first is the pseudo forest polytope. So that's generated by forests of a graph where we add another edge to make a cycle of that graph. And that turns out to have polynomial extension complexity as well. There's the even cycle Metroid. So we start off with a tree, and then we add another edge to make a cycle, and we have the additional constraint that the cycle created has to be of odd length. And I haven't got quite as far, but it seems to have the same results. And then the last one I've dealt with is the vertex matching polytope. So we're considering a matching on a graph, and we're just concerned with which vertices get matched in a maximum matching. So in this case, if we're representing this in, say, 9-dimensional space, each of these green vertices has value 1 and the black vertex has value 0. And this also turns out to have quite a compact formulation. So that's kind of how it relates to my current work and the theorems I've been using. But yeah, that's my presentation. Yep. Yeah, it's about half a page, and you're right. It does follow from the previous theorem. So another way you can define the non-negative rank is a factorization of M rather than a sum of matrices. So you can come up with a 4x3 and a 3x4 matrix, which factorizes M, and you can, with this formal definition of the communication complexity, you can turn these transition probabilities into rows of that matrix essentially, and it's the same thing. Yeah, so there's a number of different programs that work, and some of them are always going to be vertices, and some of them, like interior point algorithms, aren't necessarily going to be. And there's another question you have to ask, which is whether your polytope they're representing is even going to be integer in the first place. So you might have vertices that are non-integer, but it looks like the integer points agree. But yeah, it depends on the algorithm you run, and I think for the ones which give you definitely like a worst case linear result, it's not necessarily going to be one of the vertices. But what's tended to be used in applications such as the simplex algorithm, that will always give you like a vertex on the polytope.